Oh, okay. Paul, whenever you want, I can introduce you, and then you can go on. I'll give a brief introduction to somebody who doesn't need one.
Yeah.
That sounds so
So,
great.
Yeah, the lobby's only just opened up, so it might be worth maybe waiting a minute so everyone can get in.
Yeah.
give it a
But
minute.
yeah,
What do you want to
they are
try?
slowly
Okay,
trickling in.
46 people are coming, are pouring in now. Have you started sharing your screen, Paul? Okay, let's see. I'll do a quick introduction.
Yep.
Okay, welcome everybody. I have the distinct honor and pleasure to introduce my good friend Paul Debevec, who is a Academy Award winner, and he is now at Netflix, showing them how the future will look like in terms of games and virtual characters. And I don't think he needs much of introduction from me because Paul is very well known for his multiple technical roles in a lot of Hollywood blockbusters. So, Paul, thank you so much for your time and sharing your wisdom and insights with us. And thank you for your keynote to VR 2022. You have the
Excellent.
floor.
Cool. Can you hear me, Joaquin?
Perfectly.
Wonderful. Well, welcome everyone. It's a huge pleasure to be here. It's a huge pleasure that we're having such a great VR, IEEE VR conference, and to be able to give one of the keynotes and talk about some of the virtual reality work that I've been involved in over the last few years. I'm going to go ahead and share screen here. So I'll share screen 2. We'll see a picture of a light stage there for just a moment. Do you see that?
Yep. It's working.
And let's see if we can see some slides. And hopefully that's got slides and email, website, and such. And my title of my talk is Light Fields, Light Stages, and the Future of Virtual Production. And I'm going to talk about some stuff that I did at USC ICT before I went to Google to join their Daydream group. And then more recently, last summer, I actually switched to working for Netflix. And one of the things Netflix does is virtual production, which in some ways is the application of virtual reality technologies to the film production world. And I can kind of hint at some of the work that's going on in those areas. But one of the things that sort of pulled me into working in virtual reality with both feet is a influential conference that was put together by Professor Joyce Farrell from Stanford in the science seminars. And this was in early 2015. Virtual reality was in full swing at that point. Lots of investment going on. And she put together a very interesting workshop on light field imaging. And so there were lots of talks about light fields, but the huge elephant in the room at the time was virtual reality. And it seemed like you wouldn't really be doing your job right if you somehow didn't talk about how your talk topic was relevant to virtual reality. So this is a slide that I put together for the end of the talk, which was the idea of, well, if we're going to record light fields and then look at them in virtual reality, which certainly seems like a good idea, how would you do it? And the exciting thing is with a headset, since it's 6 degrees of freedom tracking, that in theory, you could use your own natural human user interface of just moving your head around to explore a scene, if it were possible to change the viewpoint on video that's already been shot after the fact, determining combined of how your head is actually moving in the scene. And certainly part of that would be to try to successfully record the video from all of the different angles that you need to record that video from. And so my idea was like, well, let's just build a ball of cameras. It'll be about 1 meter wide because that's about as far as you can move when you move left and right in your chair. And that maybe just do it out of a bunch of GoPro cameras. I noted that, you know, this is a lot of data to take off, but that you should be able to try to get all that data and then come up with some representation you can stream and put yourself inside of a light field. So that was the vision. And basically, it was this part of this talk that I gave that led to me getting hired by Google Daydream and some of my best team members from USC ICT. And one of the things we got to work on was VR. Now, we didn't go straight ahead to just building that camera because there was a lot of engineering to do. So we tried to explore some other possibilities and just starting to play around when we had a small team. One thing that kind of inspired me as maybe a quick and dirty way to start getting light field video from all these different angles would be to use a mirror array. And it turns out there's this sculpture, I don't know if it's still there, but in Boston Logan Airport, there's this kind of array of mirrors that's an art exhibit. If you stand in just the right spot, you can see yourself reflected back from tons of different angles and photograph a selfie of yourself and basically in one shot get a light field. It's obviously pretty small, but I wondered if that's something that we could build and at Google. And it turns out we had a 3D printer and I found a neat little mirror that had just the right amount of curvature so that if you look at a reflection in one of these little mirrors, they're designed that you can kind of tape them onto your rear view mirror, driving in your car and get a wider angle. From a distance, you basically see a 45-degree field of view out of this mirror. And I worked with Jay Bush in our group to build 3D prints that would kind of angle all of these to converge so that if you photograph them from one angle, you could photograph a person, say, sitting at a desk from a whole array of angles at the same time. And we were fortunate because this was fall of 2016. There was an election in the United States going on that some people may have heard about. And because of this, there at the YouTube space, which is part of Google, there was a set that was built up of what the president of the United States Oval Office looks like. And if you called in a favor, even if you weren't a YouTube creator, you could actually get on that set and shoot some video for your project. So I went over there with my teammate, Graham Fife, and we put on suits and took turns being the president. And I set up this array of mirrors in front of the Resolute desk and then photographed it with a very high resolution, like 6K red camera back here. And you can see us actually doing the shoot. So the mirrors are up there at the front. I'm recording the red. And you basically get all of these views of your person at the same time in the same frame. We're synchronizing the audio. And then this is what we actually ended up with. So you may be able to hear this. Graham is actually, saying an important line of dialogue in his presidential speech. And we get it from 5x5 array of views, and we shot light fields with that. We internally processed a little bit of that. It wasn't a super high quality light field, but you could basically move your head about this far and this far back and then play it back. We did this by computing depth maps between the views and view dependent texture mapping to move between. We decided at this point that maybe the best thing to do, since VR is also very panoramic, is to maybe not focus on video, but focus on getting the full field of view all the way around you for VR, and maybe focus on still scenes. So like maybe you'll go into an interesting room, you'll rotate the camera around, and then be able to photograph a light field of the room from all those different points of view. And to do that, we were lucky that there were extra versions of this collaboration between GoPro and Google's Daydream group called the Jump Odyssey 360 stereo camera that has 16 very well synchronized GoPros. And we grabbed one of these that's normally used to do 360 stereo all the way around, but we kind of pulled one apart, built some new 3D prints, and put a motor on it, Jay Bush and Shuming Yu helping build out the structure, and made it so that in about 30 seconds, this camera array would rotate around and kind of virtually photograph that full sphere of camera views that we wanted to get. And if you take a long exposure photo of it, it kind of looks like the Death Star if you leave the power lights blinking, which was fun. And the result that we got with this is a light field that we could generate novel points of view from. And the whole idea of light fields, if you're not familiar with them, is that if you want to kind of explore free space anywhere in a volume and generate photorealistic views of what a scene looks like, no matter how you move your head in this volume that you can see over here, that at any point inside the sphere, if you look out toward the scene, the rays of light that you need to build up that image from this virtual viewpoint actually at some point all had to cross the threshold of where the camera array is. And a lot of those rays were actually directly recorded by the camera array. So like this ray here, that's at the top of the image you need for this orange field of view, was shot from this camera, and this ray lower down was shot from this camera. And with some view interpolation techniques, you can synthesize the intermediate rays that would have gone between the cameras, and you can synthesize quite accurate images of what a scene looks like from any point of view inside here. And we worked on algorithms to do this in real time. So to get some good subject matter, we went to a bunch of cool places. And one of the best kinds of scenes we got were, of course, pictures of people sitting in very interesting environments. And our high point of that was this, this couple named Sherry and Gonzalo. They live in Venice, California, and they have a really funky, reflective mosaic tile house. And we did some portraits of them amongst their creation. They'd have to stay still for about 30 minutes or 30 seconds or so. And we would actually, I put this piece of green tape so that they would follow the light field array as it went around. And the resulting kind of light fields that we got with virtual viewpoint generation looks something like this. So normally in a VR headset, you could actually move around with 6 degrees of freedom. This is just an animation of showing that range of virtual viewpoints going back and forth. And you can see Sherry and Gonzalo from novel viewpoints. It's very smooth. You can see interesting reflections in the window behind them. So view dependent reflections work out. And if you look carefully at their eyes, it always looks like they're looking back at you. So you kind of feel present in the scene, or like, you know, they're responding to your head motion. And that's due to the result that I had them look at the camera array as it rotated around. And that produced this result of kind of this living 6 degree of freedom light field portrait that we got. And if you want to see that for yourself and you still have an Oculus Rift S or a Vive, you can go to the Steam store and download Welcome to Light Fields for free. And it will take you on a tour of lots of environments with light field technology from Google Daydream that includes Sherry and Gonzalo. It includes the Gamble House in Los Angeles, and a tour of Space Shuttle Discovery from the Air and Space Museum. It's about a 7 or 8 minute experience, and it's pretty fun to do. And we put that out in March of 2018. And with that thing being reasonably popular, thought that's great signal. Let's continue on and try to build a light field video camera and a light field video process for virtual reality. And at that point, it finally felt ready in this, you know, solve before you scale progression to build out the array of GoPros. At this point, actually, it was an array of Yi 4K cameras. You can see this here on the left. This is about 1 meter in diameter. We found an acrylic hemisphere, drilled holes in it in the right positions, poked the little GoPros in, and made little 3D printed brackets. And these Yi 4Ks were nice because we could take 46 of them and kind of start them all recording at the same time with something kind of like a sync cable. And if you go to this website that's down here, this is linked from my website, debevec.org as well. You can actually download a demo that will play in your VR headset, or you can even just do it in the web browser and see video of scenes shot at 30 frames per second that you can move your head around in for about 180 degree field of view. And I'll show you a video that shows some of these results. So this is what we shot of our friend Libor, who worked at the YouTube VR space. And this was shot with that rig. We called it the Sentinel rig. And these are virtual camera moves rotating around Libor. This is our artist in residence, Alexa Mead. This is Libor being a little bit of a pyromaniac in his driveway. And at any point, you can see that we can pause the video and we can move the viewpoint around after the fact for about 1 meter, which is about as far as you can move left and right in your chair. One of the big challenges is that, you know, the raw data to produce this is 46 video streams simultaneously recorded on these cameras. Streaming, you know, one high quality 4K video stream is kind of a lot of data. I like this one because you can see the reflections in the sand and the view dependence for that. It's pretty convincing. So we had to come up with some representation that would compress 46 video streams into something a lot smaller. And obviously there's a ton of redundancy in these video streams. They're all slightly different points of view. So what we did is we used a deep learning algorithm that's kind of an antecedent to what are now known as neural radiance fields, but it's called the Deep View algorithm, led by John Flynn in our group, that transforms this array of viewpoints into a stack of RGB alpha images. And since we're doing a 180-degree field of view now, we actually use spherical shells. The closest spherical shell is about a meter away from the cameras. The furthest one is almost infinity away. They're spaced out in depth. Those are our 46 original camera views that we've got. Here's our neural network, which turns it into this stack of RGB alpha images, which is trained in a way so that it can reproduce not only the original images, but training data that was shot of other scenes of what the intermediate views look like. And that was a little pass through all of these slices of the scene. So when you view it from the right position, it reconstitutes the scene. It has good soft edges, and it has a bit of view dependence because reflections end up being placed deeper into the scene with a bit of transparency of the front surfaces. So if you look at that TV in the back, the reflection moves around because it solved it as just being at a different depth. And then we take this like 120 layers, we compress it down to just 16 layers with depth maps. So we can still have some things being in front of others. And then we make a texture atlas out of it. There's enough temporal consistency. And we compress the geometry using a Draco package. And this becomes an entirely streamable thing. Right now, it decompresses and plays back on PCs. We did at Google have a version that could run on a mobile headset as well. So there was nothing fundamental, important, difficult about that. And you also got astoundingly good depth maps per every scene as well, as we've also seen in some of the subsequent neural representations of scenes that you can get out of this here. So that was very exciting to be able to kind of see this project through to completion and get it out there. It was published at SIGGRAPH, SIGGRAPH Asia 2019. And the following summer, I actually shot a bunch of new light field video with a new camera rig that we called Brutus. It was made out of these compact cinema cameras, which also synchronize very effectively with each other. And I shot all this in my backyard because at the time it was the pandemic, and so I invited friends who could do cool stuff to my backyard in order for them to perform. And the result is that we have some performances shot with very high quality cinema cameras with a wide field of view. And we have here Qishan playing a Chinese violin called an erhu. And this is some data that we hope to be able to publish soon. But if you're interested in doing light field video research, please reach out to me, debevec@gmail.com, and there might be a chance to work with some of this data. A little bit of specs about our rig are here in terms about like how the cameras were arranged and what their orientations were, the fields of view of the lenses. And we not only got Sichuan, but we got some bagpipes, we got our artist in residence, we even got like a little dramatic scene, mostly shot in my backyard because again, this was the summer of 2020. Moving forward, at some point, Google became even more interested in augmented reality than virtual reality. And part of that, of course, was the success of this Pokemon Go game, which actually came out of a Google-sponsored project from Niantic. And it was really fun to see, digital characters that we know and love kind of composited in real time on your cell phone to look as if they're actually right here with us. And the fun of this is that they look like they're standing on the ground in the same place you are, but it's not the most realistic kind of composite that you could possibly imagine. The issue is that we don't really have professional visual effects artists adding these Pokemon characters to the scenes. And as a result, maybe the viewpoint kind of matches, sort of, but the lighting certainly doesn't match. And if you look at what a professional visual effects artist would do with a Pokemon character to put them into a scene, it's going to look a lot better. This is actually a scene from a Pokemon movie called Detective Pikachu. And you can see that there's actually quite accurate illumination on the characters, and you kind of believe they're part of the scene. So in our group that was researching new techniques for virtual and augmented reality, we wondered, is there a way that we could get lighting that's this accurate? And, we thought back to our earlier work that kind of one of the gold standard ways of lighting something accurately into a scene is to capture the light of that scene and then illuminate your computer generated objects with that illumination. And these are results from 2 different scenes, rendering with natural light and Fiat Lux, that captured the light in the UC Berkeley Eucalyptus Grove or St. Peter's Basilica in a way that the illumination can be simulated on synthetic objects pretty accurately. So we don't have a way of actually going out and sending a visual effects crew to photograph high dynamic range images of mirror balls. So we had an idea that maybe this is an opportunity for some deep learning to try to guess at what the lighting of the scenes should be. This is going to be a little bit of a problem, because take a second to look at what the images in a cell phone actually look like. So what you can see here is that the field of view of a cell phone camera is pretty small relative to what you would have seen on a mirror ball to capture the lighting, or a 360 panorama to see all the different directions that important lighting can come from. On a typical cell phone rear camera, it's actually only about 7% of the scene that gets seen of that full solid angle of the sphere. And it's not even the most important directions for lighting either, right? Like lighting importantly tends to come from above, and you're seeing actually what's behind the object. Another problem is that the cell phone doesn't have, high dynamic range imaging by default. Maybe it does some HDR to tone map it, but the photo that you actually get out of the phone isn't particularly HDR. And so we know that if you take a low dynamic range image with clipped highlights, and the light sources, you don't really know what their intensities are because they've been clipped to the white point of the imaging system. If you use that to do image-based lighting on an object, you'll get, an inaccurate result. This is the result of taking, this lighting environment, lighting a CGI object with a low dynamic range clipped version of it and the full dynamic range. And you can see there's a very big difference in how bright it appears and how bright the highlights appear. So we had to figure out a way to use cell phones to capture training data that would somehow be able to infer what the 360-degree high dynamic range image would look like that you could illuminate those objects with. And to do that, we built a little rig that we attached to the cell phone. We actually built a few of these, where there is an array of 3 spheres held out on a carbon fiber lightweight stick. And the reflections off of those 3 spheres basically tell you everything you need to know about the 360 degrees of lighting around you and the full dynamic range of the light. And in our training data, after we had people run around different interior and exterior environments, we get lots of examples of this is what the background looks like. And through these spheres, the mirror sphere, the diffuse sphere, and the matte silver sphere, we get a record of what the high dynamic range illumination is. So if you just kind of, clip off this bottom section with the spheres, then you can see that this is our training data. If this is what the background looked like, this is actually the ground truth of what the lighting should be. And we got about 50 million images. We just press record on the camera and walk around, and then we're getting 30 frames per second of training data. And so these are some of our interiors and exteriors. And without that much effort, we got a ton of training data. And I think everyone can see where this is going. You then train a network so that if you show it a new background image that you don't have the lighting for, it will hallucinate what that lighting is, what that high dynamic range 360 degree, not very high resolution, but you don't really need that for lighting, would be for that scene. And presumably the network is doing something like I don't know, recognizing shading in the images, guessing at the depth, which surfaces are brighter or darker, maybe a tiny little bit of object recognition. Who knows? It's up to the network to figure it out. It actually kind of figures it out, and it comes up with pretty plausible lighting for most scenes. And so these are some results of that rocket ship model that have been placed into some real environments, interior and exterior. I guess these are the exteriors here. We'll see some interiors in a second. And it actually matches the lighting in there pretty well. It's not as great as if, you know, Industrial Light and Magic or Weta Digital put it in, but it's pretty close to, it's certainly a lot better than, you know, what we had seen in early augmented reality applications. These are a couple of results of some other environments as well. And so this actually shipped in the ARCore library that you can get on Android phones. It's called Environmental HDR, and it'll give you the lighting of any of the scene that your camera's pointed at, an estimate of it in a couple of different forms that can be convenient to render your objects in. And it also, the model was made so that it would run on a mobile phone okay. Alex Ma and Chloe Legendre were two of the main contributors to that from my group. When we were doing all of this, we actually realized that, you know, we had to be aware of, like, if there are going to be people in the scene or not. Like, one of the things is you need in your training data, you want to be aware of, you know, not accidentally take pictures of people. So I think everything we trained on here, we made sure that didn't have people in it. We actually realized if there's a person in a scene, the person's face and head actually reflect the light of the scene. And that actually can tell you a lot about the incident illumination in the scene. Obviously, everyone's face is different, but there's enough similarities to them that you might be able to basically use a face as your light probe to estimate your HDRI map. And one of our follow-on work that we did at SIGGRAPH Asia 2020, showed there by Chloe and Alex and our other collaborators from the Augmented Perception group, was to try to use a face as a light probe. And like a lot of ML projects, you have to ask yourselves, well, how are you going to train your algorithm? You certainly can imagine there's a neural network where you give it a photo of a face and it outputs a light probe. But to do that, you have to train it with lots of images of faces with the ground truth of what that light probe actually is. And how are we going to do that? Well, it turns out we're pretty lucky because we had spent a few years at Google building a light stage. And one thing that light stages can do is it can simulate what a person would look like under different lighting environments and in different backgrounds. It's kind of just exactly what it's there for. And what we did is we invited about 70 different individuals to come by our laboratory, and we photographed them in the light stage from lots of different lighting angles, lots of different viewing directions, lots of facial expressions, and lots of different clothings and accessorizations and hats and glasses and things like that to try to get a lot of training data. So these are our 6 viewpoints that we had for everybody. And these are a subset, 24 out of the 331 lighting directions that we got for everyone. People would have to stay still for about 6 seconds. And there's some optical flow to kind of line them back up if they move a little bit. And when you have a person's face lit from every direction that light can come from, you can go back to the classic image-based relighting technique from SIGGRAPH 2000, where you multiply all of these images lit from different directions by the colors and intensities of the light in the environment. You add them all together, and that produces a version of the person lit by that lighting. And it's quite accurate because it's all just based on image superposition, and you get the right shadows and highlights and self-reflections and self-occlusions and everything. There's that data set there. This is our undergrad from way back when, lit by that light. And we also, when we photographed all of our light stage data, one of our lighting conditions turns off all the light on the person and we light the background behind them. And that allows us to then get an alpha channel. So we can also put a background in that is the background from that HDRI map. So if we go one slide forward, what you can see, all of these are images of the people who came to our light stage. But we've used image-based relighting and image compositing to make them look like they're somewhere else. We've lit them with the light of another environment, and we've put the background of that environment in there. So hopefully at first glance, it kind of looks like it's just, you know, people hanging out in various places. But the magic now is that for each one of them, since we told the algorithm what the lighting should be, we know the lighting. We have the ground truth of all of these images of what the 360-degree incident illumination map, the HDRI map, should be. And now we can start to train an algorithm to try to guess what that is from an image of a face that we don't know the lighting yet. So this is how our network will work. We'll put in an input low dynamic range portrait here on the left. We'll run it through our neural network, and then we'll try to predict what the lighting is, the cost function. If it's training data, we'll subtract it from real lighting, and we'll try to minimize that difference. And Chloe actually put in a multi-scale adversarial loss, which kind of synthesizes high frequency content of the mirrored sphere as well. So here we go, our estimated lighting. We have our input. These are two people where they were held out of the training, and we didn't tell the algorithm what the lighting was. We just asked it what the lighting was. And this is the lighting that it estimated here next to them. And then we took two faces and we lit them with this lighting to see if it looks like these faces are lit with consistent lighting as the people who were photographed before. And generally speaking, it looks pretty accurate. It looks pretty believable. We can kind of further validate that if we take these same people here and we light them with literally the ground truth lighting that we know was illuminating these people, because that's what we told the algorithm to light these people with. And the fact that this image here looks so much like this image here, and this image here looks so much like this image here, is the sign that the algorithm is actually coming up with really surprisingly good estimates of lighting off of faces. And we did one more test where this is like using the full resolution of the lighting. Here, if you only use like the first 9 spherical harmonics of the light, you can see you get a considerably duller appearance of the skin, but it's overall correct. So if you like lighting with 9 spherical harmonics, go ahead. You won't get, you know, good speculars in the skin or the highlights accurately or not, but that will work. Something that was very important for us as well is that this would work for a range of skin tones, and that if you had a person with like a rather light skin tone, you wouldn't want the algorithm to estimate that there's a lot of light in the scene just because the person's reflecting a lot of it. Likewise, a dark skin tone, you wouldn't want to think it's a dark scene just because the person's absorbing a lot of the light. And we had a rich enough training data set with enough diversity that the algorithm figured this out. And so you can have a person of one skin tone estimate the lighting, light somebody of different skin tone, and the average color of their faces will actually be quite different and in proportion to their original skin tones. In fact, actually, you can use a quick variant of this to get a good skin tone estimator, for example, if you're trying to recommend a particular cosmetic that might match somebody's skin just based on a photo of them. Here's another result in motion. This is Jay Bush from our group, and she's holding a sphere. The algorithm's estimating the lighting off of her face and then illuminating the sphere with that. And that's working pretty well, matching. Here's someone where we estimated the lighting off of this person's face and then used that lighting to light a photoreal computer generated model of another person ours. This is an astoundingly good CGI model of a human. So let's just believe for a moment that's possible. It is, if you've got really good artists. And we lit this CGI model with estimated that light. It matches pretty well. And here's like another example where we pulled light off of this person, lit this person. You can even do it with dynamic illumination. So basically with this person here, we're estimating lighting off of her face, and then we're lighting the background. These virtual balloons whether lit pretty consistently with the light on her face and the light on the background, which is exactly what we hoped for. And we hope that this kind of technology will get into augmented reality applications more and more. The last major thing I wanted to talk about today kind of turns this problem around, where instead of using a face to get the lighting, we have the lighting, but we want to put it back on the face. And we don't necessarily want to have to do it by photographing the face under one light at a time and then illuminating everyone after the fact with image-based relighting. If you're making a movie, you might want to be able to create a version of the scene wherein you're able to, just a second here, I think I might have to restart PowerPoint because it got a little too excited here. But what we're going to talk about are ways to be able to reproduce illumination on people. Now, if you've been following what's been going on in the Hollywood visual effects community for a little while, then you might have seen that this whole area of virtual production has started to get very excited about illuminating actors by surrounding them with LEDs to light them with the light of virtual sets. And this is something that we've been interested in our group doing for a while. And in fact, the first paper that we published on this was at SIGGRAPH 2002. So it's actually the 20th anniversary of the SIGGRAPH paper. And we surrounded actors with LED lighting that was actually driven by DMX over USB, and we would illuminate them with image-based lighting environments, HDRI maps. And so you can see here are some of our friends that have been lit with the light of the Eucalyptus Grove, the Uffizi Gallery, Grace Cathedral. And if this video will play here, hopefully we're optimized for video now. We basically sample those images in the process that's called pixel mapping now to get the colors of the DMX lights. We play back the lighting. We actually built an infrared compositing system. So there's a field of infrared light and a beam splitter camera to get the alpha channel. And then we can do a really good composite of the actor back onto the environment. And nowadays, there's lots of virtual production stages that do this now using higher resolution LED panels, which weren't available when we first started doing this 20 years ago. Something that has remained mostly the same, though, is that the color rendition of these LEDs is not the best. And what you're trying to do with these colorful lights that you've surrounded people with is to simulate what real world illumination would look like. And real world illumination is like, I don't know, incandescent light bulbs or daylight and skylight. Most of these lights are pretty broad spectrum. They have energy all across the rainbow. And it turns out, if you take a look at the spectrum over here on the left, the LEDs that are either in an LED panel or in one of these DMX lights that we bought 20 years ago only have like a little peak of spectrum in the red, a little peak of spectrum in the green, a little peak of spectrum in the blue. And because of how the cones of the human eye work, you can simulate a very satisfying gamut of colors by mixing different amounts of red and green and blue. But it lights things funny because it's missing a lot of the spectrum in the yellows and the oranges, and there's a little dip between blue and green. The red happens to be like kind of at a strange, too close to near infrared version. And so if you light somebody like our intern we had for the summer 10 years ago or so, it turns out skin tones tend to look wrong. And a lot of clothing colors tend to look wrong. Skin in particular, whether it's a light or a dark skin tone, picks up too much red. And light skin tones actually pick up a little bit of extra blue. So if you step onto one of these virtual production stages, all of a sudden you've turned pink, and you turn pink relative to like a white shirt you might be wearing. So if you color balance based on the white shirt, you're still too pink. If you light with broader spectrum illumination, you'll actually get a considerably different color rendition, even if something that's white in that stage looks exactly the same. So this is a problem that we anticipated, and we built a light stage lighting reproduction system some years ago that actually put red and green and blue, but also amber and cyan and white LEDs on every single light source all around the actor. This is Light Stage X3 at USC ICT. This is Chloe Legendre. She worked on her PhD thesis for finding a way to drive these lights appropriately. And what we were able to do actually is figure out a way so that if you've captured your HDRI map in an environment, which probably you've done with an RGB camera, so you get a red channel, a green channel, and a blue channel of the lighting. But if you also know what a color chart looks like in the environment, you can see in the middle here, this is the light probe we used for this project. And we have a mirror ball, we have a dark plastic ball, so we don't have to shoot as many exposures to get the HDR. And then we also have these miniature color charts aimed in different directions. These basically tell us not only the RGB color of the light, but important information about the spectrum of the illumination, the spectrum of the illuminant that you need in order to produce this lighting on the actors. And the result is that we could get and drive all 6 channels of our illumination with this recorded illumination and do it in a way that we could reproduce people's appearance very accurately in our light stage compared to how they actually looked in the environment. And these are images side by side of real actors in real environments. We captured it with our light probe. We showed that light on their faces and composited them into the scenes again. And we got a very close perceptual and actual measured match between those. So we were happy to do that. This is, of course, just with a little light stage that could do head and shoulders. But we had an opportunity in 2017 to build an entire 8-meter wide stage for full bodies or multiple actors for a visual effects company in China, which then uses this to composite actors into scenes that they never were in and light them appropriately. And I can show you a little video of visiting their space and what that looked like. So this is the multispectral light stage in Beijing. They are going to demonstrate it for me, and they have this little show that they'll invite somebody to sit in the chair, get recorded, and then they'll composite you into the show that you never were in, but they'll light you appropriately with the correct multispectral lighting to match you into that. And they even give you some lines of dialogue to say. I won't show you the whole resulting clip, but you can see that after they worked their magic and composited me in, I kind of matched all the other people in the show, although it's probably a pretty good guess as to which one of the folks might have been added in later at this point. To show you some of the work that they did for their professional work, they can do about 80 shots a day using their process, which is very impressive throughput. And here there's an actor who played a doctor, and they actually needed to replace who this major actor in the show was. And so they recast it with another person, and then they had to use visual effects to add this new guy into a ton of scenes that were already shot. So by being able to control the lighting accurately on the stage, on the actors, they got a pretty satisfying result. And they could do this for an entire TV series in a couple of months, even though it was like 60 episodes. So looking forward to how this stuff is also being used in Hollywood, we had a chance to work with Alfonso Cuarón and Emmanuel Lubezki, the director and cinematographer of the movie Gravity, to test out some of these real-world image-based lighting techniques on actors for their film. And that eventually led to the creation of one of the more famous artifacts in visual effects recently called Gravity's Light Box, which was a whole box of LED panels. And they would play back lighting on Sandra Bullock and George Clooney so that when they composite their faces into the digital spacesuits, floating around the digital space telescope, floating around digital Earth, all the lighting would match. And that definitely well-deservedly won the Academy Award for Best Visual Effects in 2013. And we've seen other groups such as the virtual production group Asura film in about 2016 to 2017, build out a huge LED volume made out of LED panels to light actors accurately. And in recent Disney Plus streaming shows, such as The Mandalorian, have been able to use this technique as well. So just as exciting as it is to be able to get the lighting right when you shoot it, now maybe we could ask ourselves finally, but could we also change the lighting after the fact? Could we change the viewpoint after the fact? Wouldn't that be a super useful tool? And that was one other project I got to work on at Google on relightable volumetric capture that has some relevance to visual effects. And I'll just quickly show this video here. In the Google Light stage, we found that we were able to record people under a pair of lighting conditions from an array of cameras. And these two lighting conditions, which basically illuminate you like a normal map, gradients of light, red, green, and blue coming from above and the right and the front, and then reversing all those from the next frame, let you record not only a texture map for your actor, but a normal map per frame. And by doing a 3D reconstruction and having kind of these relightable textures from the normals, you can composite actors into scenes where you don't need to know the lighting on them beforehand. And some of this technology actually also made it into smartphone photography as well, in the form of our project that we call Total Relighting, where if you were able to just take a regular selfie on your phone, we could use all of that light stage data of what people look like in different lighting environments to train a network to visualize what a face would look like in the different lighting of a different environment. And here you don't even need to bring the person to the light stage. So that could also conceivably become a filmmaker tool. But if you'd like to play with that today and you have Google Photos on your phone, feel free to try the portrait light feature and take a picture of yourself, find portrait light, and then you can virtually move another light source around your face and improve your own personal cinematography. So I think there might still be a few moments for questions. I'd like to thank Joachim and all of the organizers of IEEE VR this year for inviting me. I'd like to thank the various managers that I had and teammates that I had over at Google that contributed to all of this here. And if you're interested in all of this work and maybe continuing in some of these areas, we're building our team at Netflix, and we're very interested in computer graphics, computer vision, and machine learning, and the intersection of all these, and even virtual reality for filmmaking. We have a big virtual production department. Feel free to contact me, debevec@gmail.com, and most of these projects are on my website, which is listed there too. So at this point here, I'll just leave that slide up for a moment, but that's my talk, and thank you very much.
Well, thank you so much for your usually great work. I was just, maybe I should remind everybody who does not know Paul Debevec. Yes, he was the face behind Benjamin Button and Gravity, as you recall. And so welcome. You are welcome to post your questions in the Discord channel or directly here in the chat room, in the Zoom chat room. Other than well-deserved applause for Paul. I think there was a question early, and I'll start by Muhammad, who asked, will we need light fields once NERF matures?
That's a great question. I think NERF is just another great form of light field. I think that, you know, there's been a lot of representations. I guess there's a bit of a subtlety between the planoptic function, which is the 5-dimensional function of like forever. It's like the set of all panoramas in space. For any XYZ in space, it's like, what's the radiance at every theta and phi coming in? And so the original, you know, planoptic modeling work and the planoptic function, that's what that was described as. I don't think you get a fun acronym out of planoptic or something. Actually, Berkeley tried this very recently. Let's see how it goes. It's called planoxels. Go planoxels, yay planoxels, love it. But I think radiance fields, like a radiance field is basically saying the same thing as the planoptic function, but it helps you make a fun acronym. So you get that out there. I think that representing scenes either explicitly as volumes with, you know, you're actually like allocating arrays in 3D that are sparsified and such so you can take care of them, and looking at directional radiance, or what the neural radiance fields work does, puts those implicitly in the weights of a neural network. Both of those are fantastic new evolving scene representations, and they are in the process of revolutionizing computer graphics, and it's really exciting to be around and adjacent to some of that work.
Excellent. Thank you. There is another question from Eric Lacey, who says, with the big push in industry from traditional VFX rendering towards real-time rendering, is there potential for these technologies to see the light with Unreal and Unity's real-time rendering pipelines?
Gosh, I hope so. So what the reason that like virtual production and real-time rendering go hand in hand so well is they like to put the background of the scene like literally on the LED panel. So what the camera sees, the cinema camera sees on set on the background is like shown from the correct angle. And since you want to let the cinematographer move the camera around in real time, you need to adjust your viewpoint on the scene in real time for that. And that kind of means it needs to be like a 3D scene that's getting rendered in real time. All of these other technologies, they are going to help with, lighting and the composition, adding other elements to the scenes that maybe aren't practical to put onto the sets, like, smoke effects or laser fire or something. Being able to add those in real time, also super helpful. And the fact that they're essentially running, these Unity and Unreal game engines on very high-end PCs driving what's on the walls means that this is a great place to be doing that kind of work. So I think there's lots of places for that to help.
Okay. One more question. So, and I think it's correlated to one of these things. Paul, during your presentation about using humans to relight, to get the correct light from a scene, I was expecting to see Pokemons at some point, correctly relighted and shaded. And how come?
I think it has happened, and that's just my own not getting around to it yet. So one of the cool things about like launching a feature at Google is, they want to track to see if anyone's using the feature that you launched. So you get metrics back, and we got to see that this environmental HDR feature was actually getting used and integrated in lots and lots of augmented reality experiences that run in ARCore that you can get on the Google Play Store. And I believe they didn't redo the original Pokemon game, but there was some like little side story version of the Pokemon game that I saw come through, and it was using environmental HDR. So I could definitely close the story on that better by grabbing some pictures from that. That's a great suggestion.
Okay. Would you be up for a provocation from one member? Would you know a case where your model fails to produce the correct lighting? If so, what are you doing to correct it? Usual review number 2 question.
Let me tell you what I think is like kind of the hardest case that we get, where the models, it's going to have trouble producing the right lighting. I think it's pretty good at producing plausible lighting, but sometimes when we're walking around with the ground truth rig and there's the 3 spheres in front of the camera, we would walk from indoors to outdoors. And so as soon as you're like basically halfway through the door, you're still inside, but the view of the camera is outside. So essentially you're seeing a sunlit environment, but since you're not outside past the eave of the house, the spheres are still in shadow. And then you take one more step forward, and all of a sudden the background doesn't change hardly at all, but the spheres go from being in shade to sunlight. And you've just done, I think, a very confusing thing for your ML training, which you've basically shown the same background and 2 completely different versions of what the lighting can be in the foreground. And ultimately, it's going to have to decide. I always worried about that. It doesn't seem to like really mess it up, but I feel a little bad for the network, and I think we should look at that more closely.
But we have our own neural networks that react by adapting to different lighting conditions. So maybe next challenge for you would be to hallucinate retinal adaptation.
Maybe that could be like better, auto gain control that you would get. Like if you're playing a video game, Video games are rendered in high dynamic range now, right? They actually do radiosity solutions from sky models. And if you go inside a cave, it slowly brightens up. If you run outside, it's like way bright for a second, but then it brings it down. What I've seen in video games, it's very much like what you would expect a camcorder to do in terms of its auto exposure and auto gain control. I know for real, like if you come out of a movie theater in the middle of the day into the sunlight, it takes you like, at least 30 seconds before you can see correctly. That would be a much better model to have for some of these games, I think.
I guess so. Hey, Paul, one of the limitations of these virtual conferences is that you cannot experience the warmth and the applause. But if you look to the chat window, the Zoom chat window, and your channel in Discord, everybody is going ape about the quality, and you get lots of accolades here. So you did a fantastic job as usual and as always, and I'm very glad and happy that you could find the time to share your cool stuff with us at Virtual Reality. And I, for one, look forward to seeing you in Vancouver.
Absolutely. See you there at SIGGRAPH this summer. And thanks for all the emojis. Thanks for the invitation. Good luck with the rest of the conference. Great to be here.
Excellent. Thank you so very much, Paul.
Okay, bye. Thank you.
Okay, and that concludes our fantastic keynote, and on to the next session.